Okay, let's talk about the probability with dependent events. We'll use the same group of, the same sample space, a standard deck of cards. And again, we're going to draw two cards. So we're looking at the probability of getting a 7 and the probability of getting a jack. So seems really similar to what we did when we did probability with independent events. The only thing here is that we're going to specify something new and different. What we're going to say is that in this case, we're not going to replace the cards. Now, so we'll say without replacement. Now, that is the instruction you're being given. So you kind of need to be told, although I will tell you this, is that if you are not told anything, you can assume this. So you will assume this unless you are told otherwise. So in other words, if you are told with replacement, then you must calculate using independent events. But if you're not told anything, you're going to assume that the card is taken out and left out, because that's normally what we do with cards and other various things. If you go to buy a sandwich, normally you don't take the sandwich out and then put it back. And when you're dealt cards, normally you don't put them back until after the round is played. So anyways, without replacement is what we're being told. And so these events are going to be dependent, not independent. Let's take a look and see what that means. So the probability of getting a 7, well, there's 4 7s and there's 52 cards. So the probability of getting a 7 is going to be 4 out of 52. Looks kind of similar. And because we say and, we're going to multiply the probability of getting a jack. The only problem is we're told that this time when we take that first card out, we're leaving it out. And what that means is that whichever one of these 7s that we got, it's no longer in the deck. And so now when we think about the probability of getting a jack, now it's 4 out of 51 cards. Okay, so let's go ahead and do that. 4 out of 51. And so this is how we do calculations when we look at the probability with dependent events. Again, we can go ahead and do the math, and it's not pretty in this case. It's easy to reduce this, so we get 1 over 13, but 4 over 51 cannot be reduced easily, so we're just kind of stuck with this, and we get 4 over whatever that is. Looks like it is 663. So let's go ahead and put that there. There we go. And again, we could divide this and get a decimal or a percent, and the fractions and decimals and percents are all reasonable ways to represent probability. One thing I would like to remind you, as long as I'm mentioning it, is probability. I believe I said this in another video, but probability is always a number between 0 and 1, including both 0 and 1. So probability will never be like 150% or 1.5. Okay, I do want to take a moment and try to generalize, so we're going to write out the formula that we use for this. What we say is this: the probability of A and B, event A and event B, both occurring, when we have dependent events, is going to be the probability of A times the probability of B with this sort of vertical mark and A, and that vertical mark stands for given. So we say that as given. And what this means is that to calculate the probability that event A and B both occur, if one of them is dependent on the other, we say probability of A times probability of B given A. So you'll notice that that's exactly what we did here. We had the probability of pulling out a 7, and then we did the probability of getting a jack given that event A already occurred, which was whatever it was. So that's why this probability, that's why this number is not 4 over 52, because even though we know probability of getting a jack is 4 over 52, that's not true when you pull out a card before and you don't replace it. Okay, so again, we have a handy dandy little formula that you can add to your list. And it's probably pretty important to write down that this formula works for dependent events and the other formula is for independent events. Dependent events. There we go. Cool. Great.